Hi everyone, Mr. Ang here. So this is the video going through chapter 5, Turning Effects of Forces. So we've already gone through chapter 5 before during lessons. So in this video, I'm only going to be doing a quick recap of all the concepts and mainly focusing on the worked examples in the notes so as to allow us to answer questions, okay, that come up on these concepts. So we've learned in our previous chapters that forces can cause objects to accelerate. Okay, these are from Newton's laws of motion. However, now we're going to learn about how forces can create moments, okay, which will cause objects to turn. So this is a simple example of the moment of force over here, which can cause the seesaw, okay, to turn. Or this seesaw is also known as a lever. We've learned about this in primary school. I'm not gonna go through the different classes of levers. You should remember that there are three, okay? But for how levers work, we know that they all work by turning or rotating about a pivot, and forces can cause objects to rotate in order to move a load. So this is due to the fact that forces exert a turning effect known as a moment. Now, the turning effect of force is proportional to two things. One, the perpendicular distance from the pivot, and two, the magnitude of the force. Another word for moment, okay, is known as torque. So torque, you might have seen when you are looking at, for example, car shows, shows like the Grand Tour, or if you're reading magazines about cars, or reading up about engines. Okay, torque is essentially the same as a moment. However, for our context in the syllabus, we are going to use the term a moment instead of the word torque. So the formula for a moment, okay, we've already seen this in class, is that the moment is given by the product of the force applied as well as the perpendicular distance. Now, perpendicular distance, of course, is not just the same thing as distance or between the force and the pivot. It also depends on the direction of the force or the line of action of the force. So these should all be concepts that you are quite familiar with because we've gone through them in class before, okay? But we'll show some examples later on how to find the perpendicular distance between the line of action to the pivot. And of course, the SI unit for the moments is Newton times meter because the SI unit for force is Newton and the SI unit for distance is the meter. Now, the moment is actually a vector quantity. Okay, we will see that moments have two different directions, clockwise and anti-clockwise, and therefore they are vectors, they are not just scalars. Now, for moments of a force, like I said, because they are vectors, they can have either a clockwise effect or an anti-clockwise effect. If they're trying to cause a clockwise rotation, like this part over here, okay, it's trying to move the lever or this bar clockwise relative to the pivot. So this line of action has a clockwise moment, whereas this line of action here has a anti-clockwise moment about the pivot. Okay, and then the question over here, is there a moment if the line of action passes through the pivot? So we'll answer that using our diagrams here later on. But first, let us go through the first worked example. We've already gone through this in class, so very, very quickly, calculate the magnitude of the moment generated by this teaspoon used to lift the lid of a coffee tin. So what we want to do is to quickly use our formula for moments. So we know that moment is given by the force multiplied by the perpendicular distance. Now, I've also used this notation over here to denote perpendicular distance. However, that's not required. If you just put F times D, that is acceptable as well. So we see over here in our example that the force has a magnitude of 10 newtons and the perpendicular distance is 10 cm. Very important, we convert it to SI units. So this will give us then 1 Newton meter. So that is our answer for A. Now for B, what is the direction of the moment? You can see over here, based on the diagram, this is going to be a anti-clockwise direction. A further note, if you use counterclockwise instead of anti-clockwise, that is also acceptable. We are not going to penalize you for that. Both are equally valid. Now for part C, we replace this teaspoon by a longer tablespoon. The perpendicular distance is now 20 cm. Calculate the force required to generate the same moment. So over here in part C, what we have is the same formula, moment equals to F times perpendicular distance. This time we know that our moment is going to be 1 Newton meter. We don't know what the force is, but we know it is going to be multiplied by a 20 cm perpendicular distance. I'm not going to show all the steps at this point. This should be quite simple, and we will find that the force is 5 newtons, and that is our answer for part C. So you can see over here the relationship. When the perpendicular distance doubles, the force is halved in order to get the same moment, the same turning effect. Okay, this is also parallel in our real life experience. You don't need as much force if you have a longer lever. So moving on, the line of action. Okay, if we think about the line of action of a force, we are basically just extending the direction of the force. Okay, if we have a vector diagram, we are basically just extending the force and finding the distance between the pivot and this line. So in this first example A here, our line of action of this force is going to be a dotted line like this. I'm simply extending this line, and that perpendicular distance is between that of the pivot, which is the nut over here, denoted by this point, to the line. Okay, and take note that it is perpendicular, meaning that this distance forms a 90-degree angle, and that is why we call it a perpendicular distance. Now, for our second example in B, we see actually that the line of action, we extend it from the force. We will find that it passes through my pivot. And if it passes through my pivot, there is no distance between the pivot and this line, and therefore there is no moment. If we use our day-to-day real-life experience to think about this, this also makes sense, because if you are pushing directly towards the pivot of a rotating object, this does not cause the object to turn about the pivot. Now, these two examples have been quite basic. Okay, the angles have been all nicely 90 degrees. So what happens if instead of 90 degrees, we get a weird angle? So let's have an example here. If I have a plank pivoted about this point over here, and I have a force being exerted on the other side of the plank in this direction, what would my perpendicular distance be? Okay, I'm going to use a different color just to make sure that it's easy to see. Let's use green. And we can see that for line of action, like what I said earlier, what we do is we extend the line of the force. So based on this force here, we extend this line. And then from the pivot to the line, I must draw a perpendicular line. And that's how we measure the perpendicular distance. So how that would look like would be something like this. So this over here would be my perpendicular distance. And you can see that it is a nice right angle between the line of action and the perpendicular distance. So there's a rule that you must remember all the time. Perpendicular distance, line of action must be right angle. That's why we call it a perpendicular distance. And another thing that this tells us is the largest perpendicular distance you achieve is actually when the line of action is directly perpendicular to where the force is. So what I mean by that is, if I were to use another color, let's say blue, and I have a different force from the same point, how do I get my largest perpendicular distance? That would be a force like this, because then my line of action would be, let's use a different color here. So if I have this line of action, then my perpendicular distance would be over here, which is the longest possible perpendicular distance between the pivot on the left and the origin of the force on the right. So this would be a second perpendicular distance. Now moving on to our second worked example, you see over here a figure with a spanner exerting forces to this spanner to tighten nuts and bolts. So where is the pivot in this scenario? Remember, the pivot must be the object which everything rotates around. So over here, okay, if you've used a spanner before, you will know that what it is doing is turning the nuts and the bolts. So our location of the pivot would be here. Okay, we can label it O. This would be where the pivot is because everything is rotating about this point. Now for part B, calculate the moment about O due to the 10 Newton force. So we then apply our simple formula again. Moment equals to F times perpendicular distance. This gives us 10 Newtons multiplied by 0.25 meters. Okay, just do a quick conversion in your head, 25 cm to meters. And then this will get us 2.5 Newton meters. And that would be for part B. Now for part C, calculate the moments if this 10 Newton force was pointed directly towards the pivot. Like what I said just now, okay, if it were pointed directly towards the pivot, the perpendicular distance equals to 0. So we don't even need to calculate it. Anything times 0 would just simply be 0. So our moment would be 0 Newton meters. Okay, to make it very, very clear what that would look like, it would be a force, instead of pointing downwards, would be pointing inwards. Sorry about that. Okay, so this force would not cause the spanner to turn at all. Okay, and again, you just think about our real life experiences. Okay, that is something that makes sense. If you push directly towards a pivot, the object is not going to turn.